and then we can get started. Okay. Welcome everybody. Just wanted to start today by again just starting with a quick recap of what we did last time around, and in particular, the the thing that we explored last time is the solution in terms of separation of variables. And in particular, we looked at separation of variables, and in this case, where we assume that the solutions are of a separable form. And so in Cartesian coordinates, we have that potential is just a function of x times a function of y times a function of z. And we can then see that we can reduce the, so we can now turn the Laplace equation, which is just the nabla squared, is just partial x squared partial y squared plus partial z squared by 0 equals naught. We can turn this into three ordinary differential equations in the form of x double prime x equals n squared. And then we got y double prime y equals m squared. And then we've got z double prime z equals L squared, where in this case n squared plus m squared plus L squared 0. Okay, and so ultimately we ended up finding solution in the form where, sorry, I keep hearing an echo. Okay, I think this is. Okay, I think this is better. Okay, indeed. And so by writing it of this form, we can actually see that we can write the most general form of this equation in terms of cosines and sines, or even hyperbolic cosines and sines. So it's just exponential functions, depending on whether they are complex or not. We can have our solutions in that way. And so in this case, what we have here are simply that x is as a function of x can be written as a e to the well, I can write nx minus nx. I can write y as a function of y as c e to the m y plus d m and so on. Okay, and then I can superpose these solutions in such a way that for any value of n, m, and l that are allowed, we can make a superposition of their solutions. So for example, we can write that the solutions, and so we can write the solutions in, for example, a form where it's L, N, M, and we can do L big X, now labeled here, and then Y, what did I use? X, N, M, N, M, Y, Z, L, Z. Okay, because in this case we are considering a linear equation, and so the solutions can just be a linear sum of all the allowed solutions. And then what we're after is then just match the boundary conditions. Match the boundary conditions in order to find ourselves a solution. So this is more or less what we looked at last time around, and in particular, we showed an example where we have a square kind of potential constraint, where on one side phi is kept at 0, which is just the conducting plates, and then one side is kept at some phi naught, and then we can solve both problems, and we can use the Fourier series in order to find all the different constants in this infinite series. And we wrote it, again, this final solution as an infinite series. So this is a particularly powerful solution, especially if you can exploit the symmetry. And so today what we're going to do is we're going to look at two more of these examples, but now using the appropriate symmetries. And so instead, what we're going to do today is we're going to look at plane polars. So today, we're going to look at plane polars, okay, where we just have an r and a phi, in which case the Laplacian, 1 over r partial r, r partial r, plus 1 over r squared partial squared r phi, or we're going to look at spherical polars. And in which case the solutions are a different form. Well, the Laplacian is of a different form. So the Laplacian spherical polars is just given by this 1 over r squared, okay, r theta phi. Here we're form this r squared sine theta partial theta sine theta plus 1 over r squared sine squared. Okay, so we're going to take a look at the same techniques that we've employed for the Cartesian case, but now in these two forms. Okay. Now, one thing I do want to note that for today, I'm going to purely focus on some of the techniques, and then for Thursday, I'm going to delve a little bit deeper into things like, for example, how to get the Laplacian in different coordinate systems and stuff. But this should be material that won't be as relevant for the midterm. At least you shouldn't have to be able to reproduce it. And so we're going to condense maybe the more important stuff, the more applicable stuff for today, and then on Thursday we're going to take a look at some of the more mathematical details that is important for you to know, for you to study, but it's not something that I can readily ask in the midterm. It's just so that I can space things a little bit better. Okay, so let me quickly open up the floor to see if there are any questions before I proceed with the main part of the lecture. Okay, nothing there. In that case, I can't stress enough, right? At every lecture I do remind you that, if possible, take a piece of pen, piece of paper, and write along with me. It's just so that you can see if you can follow some of the maths that I'm doing, which, especially some of the derivations, is important to understand the details behind it. Okay, let's take a look at our first topic then for today, which is the separation of variables. And in this case, it is for the plane polars. So the plane polar is a two-dimensional solution, where in which case, if I draw some axes like this, so I don't know which one do you want. And let's make this x and this is y. In which case, I have some particular vector here, and so this is r and this is phi. In this case, r is just from 0 to r to infinity. And phi in this case is from 0 to pi. So this is a rather simple, this is a two-dimensional case. This will help us get through the problem really to the end a little bit faster. But it doesn't mean that this is not a problem worthwhile doing. Okay, so as I mentioned in the last slide, the Laplacian is given by the following. So Laplacian, which is 1 over r partial r, r partial r, 1 over r squared partial phi. In this case, actually, let me use v for the potential, because it is actually a little bit, otherwise the capital phi can be very confusing if I use phi for the coordinate as well. Okay. And so in this case, what do I have? So if I want to separate variables, then I postulate that v as a function of r and phi is just big R as a function of r and big phi as a function of small phi. Okay, so that's always naturally our first step. And then we can plug this in. We can plug our separated solutions into the actual Laplacian. What do I get? Laplace equation then becomes 0 equals 1 over r partial r, r partial r of big R and phi plus 1 over r squared, second partial derivative of, again, r and phi. Okay, now because we've separated out these solutions, again, r is only a function of r and phi is only a function of phi. So we can reduce this by taking phi out. So we get phi over r, and then we have something that only depends on r. So we can turn the partial derivatives into ordinary derivatives, r and r prime. Plus in this case, I take big R out over r squared, and here I get the second derivative of phi. Again, the primes in this case represent the ordinary derivative with respect to the independent variable. And so here I can write this part out. Well, no, actually, it's easier to just divide by big R phi and then times r squared, in which case we have the following. We have that r over r by dr of r prime phi double prime phi. Okay. Now we have managed to separate these solutions out, and so now what we can say is that term depends on r phi respectively. Therefore, right, they must individually. This is something that I argued for last time already, is that if I want this equation to always hold, to always be zero, and each of these terms individually depend only on one independent variable, then they must be constant, because otherwise you wouldn't be, in general, be able to make this equals to zero. Okay. So indeed, if I now move on, I can now write, right, I can now obtain two ordinary differential equations, one with a form like this, right, n squared, and I get r over big R d by dr of r dr dr n squared. Okay, again, remind this is just r prime, like this. And so now we have two ordinary differential equations that we can relatively straightforwardly, at least with the methods that you ought to have learned in mathematical methods courses, you should be able to solve this. Okay, so let me quickly give you a minute or two to think about the, well, let's give you 2 minutes to think about the solutions for both. The one should be easy, and the second one, at least think about how you'd like to solve this. Okay, I'll give people 2 minutes. We'll come back. Okay, let's take a look. The first one ought to be relatively simple, right? First equation here. Can someone give me the answer to the first one? So this one over here, solution to this differential equation. Okay, maybe a little bit simpler if I write it of this form. Okay, so Pearl is saying Pearl, yet one, and Cyril are all saying exponential functions. Indeed, very well, very good. So indeed, big phi function, little phi is just given by a e to the I n phi plus b e to the minus I n phi. Okay, so that is very good. Now the next one is maybe a little bit more complex. So the big R as a function of R are dealing with a we have a homogeneous of the following form. So we've got R squared plus R R minus R squared R equals 0. Okay, so I'm just slightly rewriting this equation over here. I'm just expanding the various derivatives and I'm multiplying through by R in order to get the following equation. Now this is a homogeneous ordinary differential equation that hopefully you should be able to solve. At least you should know in what way to get the solution. Okay, so again, does anyone know how to get the solution to this equation? Write this again out for you. So R squared R double prime plus R prime minus n squared R equals to 0. Anyone know the solution to this? Or how to get it? Alex is immediately giving the solution. Solve the characteristic equation. Both are right. So, okay, let R equals to R to the power A. Yeah, all very, very good. All very good suggestions. Okay, so this is something hopefully we instantaneously recognize. Indeed, as Cyril saying, we can solve the characteristic equations. You know, and this is a way which hopefully we should all understand. The way I typically do it is we find the we first find the substitution. This is rather general, so e to the R is just e, such a way. Now I get the ordinary differential equation in terms of some t. So it would look like something like this. R equals to 0. And then another substitution. Where I leave this take R to be just lambda. Actually, take one step back. Down a little first. This here then reduces to R squared dt squared minus n squared R equals 0. And then indeed we can make another substitution of this form here in order to get the auxiliary equation or the characteristic equation, which is then gives lambda minus L lambda plus n equals 0. Such a way that we get lambda plus minus equals plus minus n. Okay, so here this equation finally allows us to say R as a function of R is just C Rn plus R minus n. Okay, so very good indeed. Alex, Cyril, Yingxing, right? So there are many ways you could solve this. You can be smart. You can do directly big R equals R to the A. That's because you can more or less guess it. But in this case, you can also take two steps because this is actually, for those who are interested, this is Euler's form. And so in principle, if you can write it in the Euler's form, it's easy to find one, sometimes two substitutions in which you can do these solutions. Okay, so again, just to go back, right? Because we started off with a partial differential equation, but by forcing the solution in a separable form, we get two ordinary differential equations that we have found one solution for right here, and we find the other one of this form over here. Okay. Now we must be a little careful because in this case we are we are thinking about, we have to think about the physics. And so one of the things though is that for the azimuthal solution, okay, phi equals a e to the I n phi plus b e to the minus I n phi. Now note that the potential must be single valued. This is actually important, right? Our solution must be done in such a way that there must be only one unique value for every point in space for the scalar potential. And so if we look at the plane polar, what do we have? Well, we have that R goes from 0 to infinity, that's fine, but we must have that phi is bounded between 0 and 2 pi. In fact, going from 0, the solution must be the same as that for 2 pi. In this case, we must have that if we make the transformation, the phi goes to phi prime equals phi plus 2 pi, we must get the same solution. So we now take a look at this form over here. And we say that, okay, well, if we add, if we make the transformation of rotating it by 2 pi, we must end up with the same, we must end up in the same point, right? We must have the same solution. This actually has an implication that it must say something about n. In this case, n is an integer. right? Because if it isn't an integer, then if I add 2 pi to it, you know, I don't get to the same point, right? This is an oscillatory function. I could equally write this in terms of, you know, I can equally write this in terms of sine, so I can write a sine n phi plus b cosine n phi. And so, you know, by shifting it to pi, you know, I must have that, you know, they end up in the same point or give the same solution in such a way that n must be an integer. Okay, and so finally we arrive at the solution, right? So the general solution. General solution is given by v as a function of r and phi, which is given by a cosine n phi plus b sine n phi r to the n plus r to the minus n. Okay, where in this case, indeed, we're writing this in terms of sines and cosines. Now, we are not entirely done yet. In fact, if I go back to my two ordinary differential equations, so one here and one here, then we've actually neglected one of the solutions, and that is when n equals to 0. So we find another set of equations or solutions for n equals to 0. So if I go back here, our two partial differential equation is this one and this one, but now for n equals to 0. So we have phi double prime phi 0, and we have that r over big R by dr, r dr by dr, 0. So again, let me give you 2 minutes to think about the solutions to these two ordinary differential equations. Okay, let's take a look at these two ordinate differential equations. So the first one, what does it give? This is a low ball. This is the easiest one you can get. The first equation on the left. Big phi equals to a phi plus b. Very good. Very well. Okay. What about the second one? You know the second one? R squared plus d logarithmic of r. Okay. Let's take a look. Okay. In this case, I can reduce this, the second equation, to by dr, r dr, r equals to 0. Then actually, r d by dr, r dr, r, which in this case just corresponds to um, r dr d by dr equals, let's do r plus d. Okay, that's fine. Look. Okay. In this case, we have that this side is r indeed. This is a constant. Okay, and I'm back. C. In this case, we have that d by dr over r. And indeed, that r equals c log r plus d. Hey, don't worry about it. Okay, that's what I mean. That's what I'm saying. This is the moment to make mistakes. Don't make mistakes in the exams, right? And so right now, this is a good point, to just come out with the answers, and even if it's wrong, hey, that's life, okay? But this is the right way to learn, right? Is to give it a try and see. Okay, so now we have again we have two of these answers, but now for n equals to 0. Okay, now again we must pay attention to this solution over here, right? Here we still must have that phi is single valued. In such a way that, for phi goes to phi prime phi plus 2 pi. So in this case, this here is not a, if I add 2 pi to this, I do not get the same answer for phi, for big phi. So the requirement that this phi must loop around, right, must give you the same answer for phi goes to 2 pi, or phi goes to phi plus 2 pi. This means that a must be equals to 0. And so now we have, quite painstakingly found the most general form. Let me write the most general form for the potential V is now given by V as a function of R and phi. So we first get the n equals to 0 solution, which is C naught log R plus D naught, right? Because since A here equals to 0, phi is simply a constant, it's just B, and I can reabsorb them into C0 and D0. Because they're still constants that I don't know, and so it doesn't matter if I redefine them. Plus, and now we have the series starting from n equals to 1 to infinity. And now I have a n cosine and phi plus b n sine phi times n r to the power n plus b n r to the power minus n. N is now any integer from 1 to, in this case. Okay. Now, bear in mind that, in all of this, must special consideration. R equals to 0. Right? And so typically when you talk about coordinates, spherical coordinates, you must always be very careful when R equals to 0. For example, the logarithmic term disappears. And also the 1 over R terms disappear. And so these are things that you must take into account when you're doing the so-called boundary conditions. Must also, in this condition here, you must check that for R equals 0, your solution actually exists. Okay, this is a good moment to break. We've actually talked a lot about these various solutions. So what I want to do is, it's after this, I want to give you an example of how to actually use all of this in our finding the right solutions equation. So let's take a slightly longer break. We've gone for 45 minutes. So let's get back at 5:25, an 8-minute break, and I'll see everyone in a moment. Okay, let's get back to it. Alex has a question. He's asking whether the midterm has been drafted yet. Um, it's customary for me to not divulge anything about the content of the midterm, but I can say that it's a relatively straightforward midterm. Nothing fancy. Just checking that you all know your basic stuff. So you can assume that it leans heavily on finding electromagnetic fields and how to solve Poisson equations. Okay, are there any other questions before I go into the example? So Cyril, do you mind posting this question in public? Okay, so the question is, will the midterm be open or closed book? You will be allowed to use what will give you a formula sheet, but we're not going to make it completely open book. But you will be allowed to use um, a formula sheet. And again, like I said, we will make sure we release that the exact formula sheet a few days in advance to the midterm. Okay, but in all honesty, I don't think you need to worry too much about the midterm. Just make sure you practice, the problem sets, that you know the basics, and that make sure that you can do some of these very basic calculations, and then I think most of you should be okay. Okay, okay, let's take a look at a specific example. So the example I want to discuss today is the following. So let's assume that I've got some you can think about it in terms of an infinitely long metal pipe, or just a two-dimensional problem. It's the same thing, it doesn't matter. So I've got this metal pipe here, and in which case I can state that this here is V equals to 0. I can lay down a call this just my axes. This is Y, X, and then what I'm doing now is I'm putting some uniform electric field. So I'm putting this metal pipe, some uniform electric field, E0. I write it twice. Okay. 0 in the direction of X. And so the the question then here is, what is V R phi outside of the metal pipe? Okay, this is this is a very textbook problem. And we last time we saw a very similar problem where, you know, set some boundary conditions. We've given you, you know, kind of the solutions in different places on different surfaces, and then you're being asked to solve it. And so in this case, again, it's easiest to first, you know, think about the problem, but reduce it to its very basics. And so the problem, of course, is to solve a class equation under the boundary conditions that 1, 0, and r equals to big R. Okay. In this case, we put the surface here. This thing here is big R. So we have the first boundary condition. What about the second boundary condition? So this is a pipe, or just a, you know, just a circle that I put in a uniform electric field. So Alex and yet one is saying V tends to 0 at infinity. Now, that could be initial guess, but again, bear in mind, right? I'm putting this circle in a uniform field, and so, you know, if you think about it, you know, I can't really. Well, I can, but it makes no big sense to put this at infinity. I don't need to. But so even at infinity, right? If I want to keep a uniform field, then it can't tend to 0 at infinity. We must think about a different boundary condition. Okay. What could this boundary condition be? Let me give you a bit of a hint. So second boundary condition, okay, comes basically from the fact that if I go very far away, okay, I don't have to exactly go to infinity, but I go very far away, what's the field that I expect it to be? What's the electric field if I go very far away from this circle? Okay, so indeed, Zhao Feng is giving me the answer I want to hear, right? Because I've put it in a uniform field, which in this case, uniform actually means uniform everywhere. It should be E0 now. It's not exactly E0, but it should be, you know, because the electric field is a vector quantity, right? So again, bear in mind, you know, it has to have a direction as well. And so the electric field, very far away, E, R is much bigger than big R, equals to not X. Now, that's for the electric field, but in that case, what do I get for the potential? Okay, so if E is a in this case is a constant pointing in a particular direction, in the X direction, then 2 can actually be rewritten as V equals minus E naught X. In this case, what is X? Well, I know that E naught, right, R cosine phi. Okay. But R is much bigger than big R. Okay. So these are the two boundary conditions that we will be using. And then again, as a reminder, the general solution is of the following form: is V R phi equals to C naught log R plus E naught plus the sum from n from 1 to infinity of an cosine n phi n sine n phi and C n r to the n plus n r to the minus n. Okay, so that is the most general solution that we have. So this is, again, right, you know, doing this in terms of separation of variables is very simple. Okay, so we look at the boundary condition, write down the most general solution, because we don't have to do the hard work. Someone has already solved the Laplace equation. Like Laplace has solved the Laplace equation, and all that we need to do is find the solution that matches these boundary conditions. And then, by uniqueness theorem, we must know that that is the only solution. Again, this is what we can simply do, and so we can more or less now look up the answer, because we have the two boundary condition. Okay? Let's take a look at boundary condition 2 first. The boundary condition 2 says that V for big R, sorry, for R that is much bigger than big R, we must have it that it tends to cosine phi. Okay, so there's a question. So Yip Choi is asking, so we just quote the general solution in the exam is okay. In fact, I'm going to give you the general solution in the exam. Right? It's not something I expect you to be able to derive firsthand. That would be too cumbersome. Unless explicitly asked, I will ask, you are simply given the solution, of course. I mean, in more or less the 4 coordinate systems that you're able to do these questions, just memorize them if you want. Okay, and so again, this technique is very useful. So if I look at boundary condition, then I know that it goes when R is much bigger than R, it must go as cosine phi. Well, I could, in this case now, say that I only need to keep n equals to 1 for an. Okay, so if I look at this solution over here, okay, now since these are just n phi's, and we know by the superposition and the orthogonality condition of this Fourier series, I know that these are all orthogonal to each other. So cosine phi, cosine 2 phi, cosine 3 phi, and so on. And so I know that these solutions must tend to only phi, cosine phi. And so I can just start off by saying, okay, I'm only going to keep A1 in such a way that V R phi is cosine phi, and then C1 R plus E1 over R. Okay? Because all the other n's, so n equals 2, would give me cosine 2 phi. And I know that cosine 2 phi cannot, mimic the symmetry of cosine phi. I know that the solution cannot contain 2 phi's. right? Because I know that on at least one of the boundaries, in this case, this is when r is bigger than big R, I know that I only have cosine phi. So here we set all the other ANs equals to 0 except for n equals to 1. And so then I absorb the A1 into C1 and D1, and I get this following solution. Okay, that's using boundary condition 2. Now, or at least that's using some of the symmetry of the boundary condition 2. Now, if I use boundary condition number 1, what do I get? Well, boundary condition 1 states that V R equals to big R for any phi equals to 0, right? Because I know that at this surface, at the circle, V equals to 0, in which case I simply get that 0 equals to cosine phi 1 big R 1 over big R. Okay. Now, I must get a general form for either C1 or D1, so I don't have to worry about the cosine in this case. So at least this term here must equal to 0, or in other words, I get that C1 R plus D1 divided by R equals to 0, or D1 equals to minus C1 big R squared. Okay. And so that gives me the following form for V as a function of R and phi is now I can put D1 in here. So I get something that's C1, and this is R squared. And so what is the solution that I have? I have that C1 cosine phi R minus big R squared over small r, like this. Okay. Now, I still have one unknown left, and that is C1. And so we can actually go back to the boundary condition 2 because we've only used, so far only used the scaling, right? We haven't used the full information. So we can again apply boundary condition number 2, which actually states the following, is that in the limit of R is much bigger than big R, cosine phi 1 R minus big R squared over small r. Okay. This here, of course, when small r is much bigger than big R, then this term here drops to 0, right? Because it's 1 over small r. So all that I'm left with is C1 R cosine phi. But if I go back, I know that from this boundary condition number 2, it must equal to minus E naught R cosine phi. So this here must equal to minus naught R cosine phi. Okay. Now just comparing this over here and this over here, what do I get? Well, I get that. Now again, this is boundary number 2. Continued. I get that 1 equals to minus naught, right? So this R cosine phi, R cosine phi. So C1 equals minus E naught. Like this. And so I can plug this again in here in C1, right? And this is my, my intermediate solution. And so the final solution is that is now in the following form: V R phi equals to cosine phi naught, minus sign here, and R minus r squared over r, like this. Okay. So again, starting from the most general solution, which again, you don't have to derive in the examinations, but it is something that you should know where it comes from. And in principle, you should be able to, given enough time, be able to derive this, right? Because it's simply solving ordinary differential equations. Okay, so having done this now, just a very quick question. I'll give you 2 minutes to think about it. So if I extend this question now and I ask, okay, what is surface charge of the system? How would you be able to calculate this? Okay. If I'm curious about the surface charge or surface charge density, how would you be able to calculate now that you know V? Okay, it's just a reminder. I'll give you a minute or two to think about it. Okay, so if I know V, then how do I get the surface charge? So Jimmy says round V round R um, times a constant. Good. Or from the Punchen, she's saying boundary condition grad V on two sides of the surface charge. In this case, because V is continuous, you don't have to take some average. You can just take it exactly at the boundary, but it is correct, right? So the surface charge is just minus epsilon naught partial V partial R, in which case my surface is at R equals to big R. Okay, so again, right, we're getting to a level now where, given some system, with some boundary conditions, we are able to solve this for very, much more generic solutions. Okay, good. Um, okay, let's swiftly move on, and let's see if we can take this a step further. Right, this was a two-dimensional example, and let's see if we can generalize this more. And I want to discuss now which are spherical polars. So for spherical polars, our situation is slightly different um, in terms of our setup. So let's draw again another coordinate system like this here. Usual Cartesian coordinate system, but now instead of doing like this, we get the system like this, where now this is R, this is theta. Oops, difficult to read. So this is theta, and this is phi. Okay, and so in this scenario, have have these three coordinates, and we can write down the Laplacian. Write down Laplace equation following form. Okay, 1 over r squared partial r squared partial r, and again I use v now for the potential. 1 over r squared sine theta partial theta sine theta partial v partial theta plus 1 over r squared sine squared theta partial v with respect to partial phi. Okay. And so this is the Laplace equation for the spherical polars. And so if we assume some separable solution, well, I write v as a function of r, theta phi as big R as a function of small r, big theta as a function of small theta, and big phi as a function of small phi. Then, just by assuming these, I have now all the tools that I need in order to solve this. Okay. So again, I'm not gonna do this very explicitly, although I'll try to do as many steps as possible. So the class equation now becomes the following: 0 equals to 1 over big R by the R squared big R prime plus 1 over big omega by big theta sine theta theta and sine theta prime plus 1 over phi sine squared phi double prime. Okay, so in this case, I did exactly the same as I did in the plane polar case, where I've introduced them. Okay, so I plugged them in here in V, and again, I just assume that, well, because I've assumed the separable solution, I can take, in this case, the phi out, or in this case, the r out. I can divide by r times phi, so dividing by v, and the appropriate factors of r, and I get the equation that looks like this. And so again, I can assume that individually this portion with just r here. I can assume that this portion here equals to a constant. In this case, I can make this lambda, in which case I get the following formula. I get the following differential equation. It's just lambda equals to 1 over r by dr, r squared r prime, this, or in other words, 0 equals to r squared r double prime plus 2r r prime minus lambda r. Okay, Now, again, we can use the same techniques as we looked before. So here we can let r equals to r to the power n. In order to get the following equation, we use n squared plus n minus lambda equals to 0. And then, we can now have, basically the two solutions is n1 plus n2 equals to -1, and n1 times n2 equals to minus lambda. Okay, and I can write these solutions in the following form: n1 equals to sum L, and then n2 equals to minus L plus 1. Okay. So again, we're solving an ordinary differential equation in the Euler form, and you can just simply use a substitution here to get the answer. So that's the first portion. Now let's take a look at the next portion here. So, okay, first. So the intermediate answer solution is now sine theta 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 sine theta plus L plus 1 sine squared theta plus phi double prime divided by phi equals to 0. Okay, and so all that I've done is here is I've substituted the solution here. So lambda, so this part I can make this lambda, and I know that lambda is simply n1 times n2, so just L times L plus 1 or minus L plus 1. And so I can just insert that in this side in order to get the following equation. Okay. So once we have that, once we have an equation like this, I can continue solving this, because again, individually, and this must equal to a constant. Let's consider this one first. This one here, and we make this n squared minus n squared. And so what we have is just phi is exactly the solution that we've seen before. So I can simply quote that solution. Take phi equals to, this is either c cosine m phi plus d sine m phi, or it's c phi plus d, where m equals to not 0, and this is n equals to 0, right? So these were the solutions that we've seen before when we looked at the plane polars. Okay, so now we come to the last portion, this portion over here. If this is minus m, then this must be plus m squared. And so now we have the following equation. So if I now write sine theta divided by big theta by d theta sine theta plus L plus 1 sine squared theta equals to m squared. Okay, now we can actually do a very simple, well, simple if you know what to do, is we can do a following substitution. So we let this mu equals to cosine theta, so that d mu d theta equals to minus sine theta, or d theta equals to minus 1 minus mu squared 1/2 d by d. 2. And then, of course, and also we rewrite this as a big M as a function of mu, which is the same as omega as a function of theta. Okay, green is hard to read, no problem. Let's do high-tech stuff. Red. How does that look? Modern technology. Here we go. And let's make this red. Huzzah. Excellent. Okay, so okay, let me make sure that I don't become overzealous. Okay, certain things. Okay, so let's continue with red. And so in this case, hopefully you can follow. So I have, this is just equals to m squared. So it's just m squared over this part over here. I do the following substitution. Again, this is something you should verify at home. I make the following substitutions and I write that m as a function of mu, which is just relabeling. So instead of big omega, I have big M. And so if I do all of this, what do I get? Well, I can now write, oops, now write by d mu 1 minus mu squared big M plus L plus 1 minus M minus 1 minus squared times N equals to 0. Okay. Now this differential equation is something that is something that I hope you, well, I hope you recognize, because we've actually seen it a couple of lectures ago. This equation, okay, the form in itself is maybe a little bit difficult to recognize, but this is actually Legendre's equation. And so I will actually expand on this, right? I will focus on this equation and the solution to this equation in the lectures to come. Sorry, in the following lecture. But it is rather technical, and we have to look at series solutions of ordinary differential equations to get something to get the solution to this. But this itself here is simply here what I can write now is solution to well, solutions are basically Legendre polynomials. Okay. And we'll discuss this in next lecture in more detail. But I wanted to take away some of these really nitty-gritty, the solution to this ordinary differential equation for next time. And now focus on more kind of the practical aspect. And so we have now, the dark green, the blue, and the red are now 3 types of solutions. And let me write down the solutions. So solutions of M are simply Legendre polynomials here as a function of mu, or big theta L cosine theta. Okay. Now, as we'll see next time, there are actually 2 sets of solutions possible. As we have also seen that, typically you got r to the n and r to the minus n, or we get cosines and sines. In this case, we also have these in terms of the Legendre polynomials, but we also have them in terms of the, associated polynomials. So in this case, we also have the Q, L, mu, or here. I'll discuss these solutions in more detail the next time, but just know that what we see here is indeed an ordinary differential equation that as a result gives you Legendre polynomials. Okay, so once we have all of this, we can now construct the most general solution that we have. Now cubes of this form. Okay, the general solution here as a function of r, theta, and phi is just a r to the L plus b r minus L plus 1. Okay, because again here what we have is that we get this is lambda, which is just n1 and n2 in the solutions over here. So we get a r to the L plus b r to the minus L plus 1. Okay, and then we have the c cosine m phi plus d sine m phi. And then we have times, and then we get the Legendre polynomials. L for particular m cosine here f u L. Okay. So again, why this Q? This Q is not very you don't often see it back because actually because in this case Q of cosine theta and L diverges. And theta equals to 0 and pi. So because the actual form at theta equals 0 and theta equals pi, this Q diverges, it often follows that f actually equals to 0. These solutions you don't typically have to worry about unless we're looking at a specific example where I am actually cutting out, I don't care about the solution at 0 and at pi. That's the only case, but generally because we are using this when we have spherical symmetry, we want to look at the entire surface of a particular sphere, and so Q diverges, all the different Q's, the functions Q's diverges, in which case you set f equals to 0. Okay. Now again, just bear in mind that the full solution we find through superposition. Okay, so that's basically it. Again, that we just following the simple steps of separation of variables, going to plugging the solutions in, getting 3 ordinary differential equations, and then solving these 3 ordinary differential equations because they all have to individually equals to a constant. We solve them and we get the general solution. And again, the full solution is then through superposition of all of these individual solutions. In this case, this L and these M are integers. Okay? But again, as I was saying, we will focus on these specific functions. This PL will focus on that next lecture. Okay, now one thing that I do want to do is give you a very quick example of using now spherical coordinates. And so we're going to take the same example that we did last time, but adjusted slightly. So again, now what we're going to do is we're going to put a sphere, and now we have a sphere like this. And we're going to again put this in some uniform field like this. We're going to put it in some uniform field, and we can call this E0 or E. It doesn't matter. We can call this direction of Z. Okay, because now it's a little bit more convenient to put this at the Z, because it's easier to define the polar angles and the azimuthal angle that way. I'm going to put this in the Z direction. Otherwise, I just have to write myself silly. So this is an arbitrary thing that I can do. So again, we are now putting this thing here at R, and here we have that V equals to 0 at R equals to big R. Exactly the same problem, but instead of having a pipe, an infinitely long pipe, here I've got a sphere that I put in a uniform field. Okay, now let's see if we can kind of quickly go through this this problem, because now I put the boundary condition 1, which is V equals to minus E, and we can call it E0 maybe for Z equals to minus E0R cosine theta. Okay, again for R is much bigger than big R. And my second boundary condition, V equals to 0 at R equals to big R. Okay, so now we can already start making use of some of the symmetry. I know that I've got axial symmetry here, in which case, if I look at the most general solution here, I know that if I rotate phi, right? If I rotate phi by 2 pi, I must arrive at the same solution. And so in this case, I only select out m equals to 0. Because if m is bigger than 0, then I run into trouble, because I get, I don't get the same symmetry out. I get something that is faster in terms of symmetry. So I can just select out the m equals to 0 case, in which case V is simply the sum of L from 0 to infinity of A L R to the power L plus BL R to the minus L plus 1, and then PL of the cosine of theta. Again, for the Q, we typically, because here we do need to consider theta equals to 0 and theta equals to pi. So the constants for Q drop out. So I get this as my solution, and so now I apply boundary condition 1, because again in this case we only need something that is proportional to cosine theta. That we see exactly the same as last time around. When we go very far away, we only keep the cosine theta solution, and so we only need to keep E0 cosine theta 0 here, because I know that P0 equals to cosine theta, right? We've seen this before, where oops, sorry, not P1. Right? Cosine theta, because I know that P1 as a function of x is just x. And so in this case, our argument is cosine theta, so the P1 of cosine theta is just cosine theta. So I only need to keep the first n equals to, or in this case, L equals to 1. So my solution now is in the form of A1 R plus B1 r 1 over r squared, right? Because I've got here L equals to 1. In this case, L plus 1, or minus L plus 1. So that's minus 2 is 1 over 2. And then here, cosine theta. Okay. Now, again, we use boundary condition 1 properly now. So at r is much bigger than r, I get the following. I here now take r is much bigger than, well, if I take r is much bigger than big R, then I know that this second term here drops out in favor of the first term here. So what do I get? I get that a1 r cosine theta equals to minus e naught r cosine theta. This is what we've seen before. So here a1 equals to minus e0. In other words, v is minus e r plus, in this case, b1 r minus 2 cosine theta. I can apply boundary condition number 2, where in this case I fill in v big R phi equals to 0. I get that minus e big R 1 big R minus 2 equals to 0. b1 is simply r cubed. Again, this is following almost exactly the same steps. I could have applied boundary condition 2 first and then boundary condition 1. It doesn't matter too much. I now know I found the last one, b1, and so indeed v r theta phi is just minus er 1 minus r cubed in this case, r cubed cosine squared. It should be squared. Oh no, wait. I put r out. Okay. Because I took r out here. Okay. So again, just following the exact same steps, I can arrive at a solution like this. Okay, and again, if I want to now know what the surface charge density is, I just take, d r at the surface r equals to big R. Okay, so this concludes more or less what I wanted to say today. So let me open up the floor to see if there are any questions, and then I'll at some point turn off the recording, and we can discuss more things off the record. Okay. So any questions? Okay. I really do hope that you will at least try these steps at home. Actually, for your homework, I'm going to have you derive the cylindrical polar version. Okay? There's one more often used, which is just a simple extension of the plane polar one in the cylindrical polar ones. So you get your first hand at trying something like this as well. Okay? But again, go home, take a look at this video, see if you can kind of fill in the gaps. Sometimes I do skip a step or two, because I do expect some familiarity with ordinary differential equations. But I'll take a look a little bit more detail into ordinary differential equations next lecture. Okay, going once, Going twice. Okay, in slide 8. Let's see. Slide 8. Actually, in this case, I can, because I can start making the dish. I can do the first substitution, which is this is a t. Okay, so r becomes a function of t because I've done e to the t here. And this is just, you can do it in 2 steps. You can also do it in 1 step. It depends a little bit what you're very familiar with. If you can see this, if you can spot it immediately, that it's an r to the power n, good for you. Do it immediately. Just highlight here an intermediate step that you can make. Okay. I don't see any other questions or hands up. Let me stop the recording then. Oh, okay. So for slide 12 is if we have dropped out r for v equals x, we have large r. So this one here, I think here. No, actually here we've simply written down what the actual field is. Okay, yes, for large r. Yeah. So when we have small r equals, very far away from this object, we recover this. So if you will, we can do the limit of r is much bigger than big R of v equals to 1. Okay, so that's why I've written this here. Does that answer your question, Harry? Okay. Anything else? At least on the record. Now, let me stop the recording here.